Okay, let's get started. Yeah, let's review what we covered in our previous lecture. So in our last lecture, we talked about Shannon codes and also the Huffman codes, right? And for Shannon codes, so what it does is that it just have the code length of this number, right? And you can see that, so this is the self-information, right? So kind of makes sense that we let the code length equal to this number, right? Yeah, however, so we need to remember that so this number is intuitively it is the self-information, right? But we derive it from the Kraft inequality, right? So it's not from intuition, okay? And we know this is less than that, okay? And we can verify that the Kraft inequality still holds in this case, okay? And then we show that. So basically, we can construct a prefix code using this length, okay? So the way that we show that is, so basically we have a code tree, and then we just count. So the number of leaves is enough for us to build the prefix code, okay? And why it is holds because this holds, right? So we use. So this inequality will guarantee that you can have a prefix code with this length, okay? And that is very important. And we also show that so this inequality is true, right? And you can see that so when n is very, very large, then we can see the Shannon code is basically optimal, okay? Asymptotically optimal, right? But for finite n, so we can now guarantee it is optimal, right? And today we're going to see one simple example that so this code is far away from optimal for finite n. All right, and basically because of that, right? So then we introduce the Huffman code, okay? And yeah, for Huffman code, so we have this merging algorithm. So basically what we do is that we rank the PMF from the largest to smallest, right? And then we merge the two least likely nodes in the tree, okay? And then we have a new node, right? And then we rank this again from the largest to smallest, and then merge the two smallest again and again, okay? Until we're done, right? We have the probability one, right? And after that, then we're gonna label the code word, right? So what we can do is that if it go up, we label it as 0. If it go down, we label 1, right? That's one way to label it. Let's make things more systematic. And one thing we need to notice is that for both Huffman code and Shannon code, so we must know the distribution, right? The probability distribution is must known, right? For example, in the Shannon code, we need this to determine the code length, right? And for Huffman code, we need to know the PMF to rank the probability from the largest to smallest, right? So for both of them, we need to know the distribution exactly, right? So is that a harsh requirement or no? Yeah, it's pretty harsh, right? So in practice, do we know the distribution exactly? Yeah, probably don't, right? So then in practice, we never use this kind of code. Okay, so yeah, let's see whether we have time to cover other kind of code that we do not need this. All right, so this is where we were in the last lecture. 6532. Today is our lecture number 21. So we're almost done with chapter 5. Okay, just a few topics left. So today, number 1, so we're going to finish about Huffman code. Okay, the construction. Okay, and then we're going to talk about the optimality of Huffman code. Okay, yeah, let's plan for these 2 topics for now. So yeah, after this, we just have one more code to introduce. It's called Shannon funnel alias code. Okay. All right. So from our last lecture, we just started talking about the DRE Huffman code, right? So when it's not binary, then what should we do, right? So basically, we say that, so what we need to do is that we need to create a dummy node, right, or a few dummy nodes, right, to, because every time we need to merge D nodes, right? So now the question is, how can we, how many number of these dummy nodes should we create? Okay, so basically, for example, if let's say D is 3, then we're going to have a tree like this, and so on, right? So the number of nodes here should be 3, right? Every time we merge 3 nodes. Okay, so now let's decide, how many number of dummy nodes do we need, right? So in order to do this, so what we need to determine is the total number leaves in the tree. Okay, and then we can decide how many number of dummy nodes do we have. Okay, so yeah, let's have some notation here. Let's denote the number of merges is k. Okay, so denote number of merges is k. Okay, and so now let's see. So for example, let's say if k is 0, meaning that we do not need any merges, then how many leaves do we have? Let's say here's the number of leaves. Or leaves is basically the number of code words, right? Okay, so if k is 0, meaning that we do not need to do any merge, right? Then how many number of code words do we have? 1, right? If you have 3, then we need to do a merge. Okay, just 1. So yeah, just 1 code word, right? We do not need to do any merge, right? Let's say if we need 1 merge, then how many leaves do we have? Yeah, if we just do 1 merge. Yeah, now it's 3, right? So because if we 1 merge, then we just merge these 3 into 1 node. Okay. So now let's say if k is 2, let's say if we need to do 2 merges, then how many nodes do we have? How many leaves do we have? Yeah, 5 is right. Why is 5? Yeah, because it's like this, right? Like this. Right, so here is 1 merge, here's another one, right? Okay, so now you see the rule, right? Yeah, let's try one more. Let's say if k is 3, then 3 merges, how many nodes do we have? 7. 2 plus 2 plus 3, right, basically 7. Okay, so now you see the trends, right? So basically the number of leaves of a tree is given by what? So it should be d minus 1 multiply k, right? And then we need to add 1 more, right? So basically here, so this is 1, this is d, and this is d, right? We need to add this 1 more, something like that, right? So basically that's the number of leaves or the number of code words, right? Remember, leaves is number of code words. Okay, is that clear? Okay, great. So yeah, from here, so basically, what we can get from here is that, so let's say in total we have n symbols in the source alphabet, right? Let's assume that we have n symbols in total. Okay, and then from here we can have that. So the number of leaves here has to be bigger than or equal to n, right? Because number of leaves is number of code words, right? So it has to be at least 1-to-1 mapping, right? Therefore, so from here we can get k is bigger than or equal to n minus 1 over d minus 1. Right, so this is the total number of merges that we can get, and from here we can also get the number of dummy code words. Okay, dummy code words or dummy nodes is what? Should be one. Oh, what happened? So basically this is what we're going to get, right? So this includes dummy code words and the real code words, right? So the difference between this and that would give you the number of dummy code words, right? So basically we can have 1 plus k times d minus 1 minus n. So that would be the number of dummy code words. That clear? Okay, that's how we find the number of dummy code words. Yeah, dummy code word is basically the code word that will assign probability 0, right? So we give an example last time that, every time we need 3 merges here, right? If it's not enough, then we need the dummy code words here. Okay, so let's emphasize that. So basically, we need to assign probability 0 to the dummy nodes, okay? And then we perform the merging algorithm. And then we're done. Okay, so that's basically the procedure. Okay, so now let's see an example. Okay, so let's see the alphabet is, we have 6 symbols, S0, S1, S2, S3, S4, and S5. And then we say the probability distribution is 0.25, 0.25, 0.2, 0.1, 0.1, 0.1. Okay, so now let's do d equals to 3, right? Okay, let's see how we can do that. So clear, yeah, if you try, probably, we need some dummy code words here. Okay, so now the question is how to determine that, right? So in order to determine dummy code words is to use this formula, right? Here we know n is 6, d is 3, right? And then what is k? Right, so it's given here, right? So basically, this is the first step, right? We need to use this formula to determine k, right? Normally we just use the smallest k. And then we use that to determine the dummy code words, number of dummy code words, okay? So let's do that. So basically, we say here, k has to be bigger than or equal to n minus 1 over d minus 1. So here, n is 6, and d is 3, right? So this is what? 5 over 2, right? Therefore, so k should equal to 3, yeah, right? We just pick the smallest, then the number of dummy symbols is 1 plus k and d minus 1 minus n, right? So that equal to 1 plus k is 3, d is 3, and then 6, right? Then this equals to 1. Okay, you can compute at home and see whether it's true or not. Okay, so then basically it means that we just need the one dummy code word, which is x6. Okay, so let's see how we can do this. So basically, how we do that is we have S0 here and S1, S2, S3, S4, S5, S6. Okay. Right, and the probability here is 0.25, 0.25, 0.2, 0.1, 0.1, 0.1, and 0. Okay, and what we're going to do is as follows. So first of all, so we need to combine the least 3 likely nodes. It's given by this, right? And then we get 0.2. Okay, and then we can make 0.2 to the top here. Right, and then we combine these 3. Okay, and then we have, yeah, here is 0.2, right? And then we have 0.5. Okay, and then we make it top, right? And then we have this, and then combine these three together. We have 1, right? And then we're done, right? So basically that's the procedure, okay? And now let's write down the code, right? So here, so basically what we do is that we label here 0, 1, 2, because we have 3 RE code, right? We have 3 symbols, and 0, 1, and 2, and 0, 1, 2, okay? And then we can write down the code. Okay, for the first one, so we just from here directly, so the first one is 1, right? And second one is 2, right? And the third one is basically 0 and 1, right? And this one is what? 0 and 2, right? And for this one is, so here is 0, 0, 0. Right, and for this one is 0, 0, 1. And last one is 0, 0, 2, right? Okay, and then we're done, right? So that's basically the procedure. Okay, any questions? Okay, so now I think you should be able to do all your homework. Okay. Okay, great. Yeah, this should be pretty straightforward, right? So now, so let's compare Huffman codes and Shannon codes, okay, to see which one's better. Okay, let's recall that for the Shannon codes, the length of the code word is given by minus log px, and then we do the ceiling. Okay, and we recall that. So the performance of Shannon code is lower bounded by the entropy and upper bounded by the entropy plus 1 over n, right? So it seems pretty good, right? And also we show that it's for DMS source. Okay, so now can you imagine what is the problem of the Shannon code? Or are there any problem? Right, let's say, what if n is 1? Right, let's say if n, the length is 1, let's say we'll consider just a binary code, okay, 0, 1 only, right? So if n is 1, then, so this number is pretty big, first of all, right? And also this can also be what? Very small. Okay, then it will make this extremely big. Something like that. Okay, so yeah, let's consider a very simple example, right? So we consider a binary alphabet, x equals to 0 and 1. Okay, so in order to make this code looks really bad, then we need to make the entropy looks pretty small, right? How to make the entropy very small? Right, we make one symbol happen with extremely large probability. Right, so now we consider the case where probability for the symbol 0, so it happens with 0.9999, right, and P1 with 0.110001. All right, okay. Okay, very good. So now let's see. So if we want to do Shannon code, so what's the length? Let's compute it, right? So log 2 P0. So what is that? Right, here is almost 1, then this guy is almost 0, right? If we take a ceiling, so that'll be 1. Not bad, right? And then how about this guy? right? So now we have a very small number here, right? So just compute it. So it should be 14. Okay, it seems ridiculous, right? So now I have only two symbols, right? So we use one symbol to code one and 14 bits to code another one, right? Which is very, very not good. Okay. How about Huffman code? Okay, so this is Shannon code. Yeah, probably Shannon will not be very happy to see that, right? So what is Huffman code? So in here, we only have, the source only has two symbols, right? And then if we do this, it's like 0.999, so that's our S1, and the 1 is 0.0001, right? And then we only have one merge, it's 1, then we're done. Okay, then we'll give here a 1, here a 0, right? So basically for Huffman code, the length of 0 and the length of 1 is the same, that's 1. Right, which is pretty obvious, right? Okay, so now you can see the problem of Shannon code, right? So because of this, so Shannon code is not optimal. Okay, our conclusion is that the length of a Shannon code may be much worse than the optimal length for some symbols, right? Because for this symbol, it's pretty good, right? It's optimal. But for this symbol, it's not. Okay, so it means that, you know, Shannon code is optimal asymptotically if we increase n, right? But if for finite n, Shannon code is not optimal. Okay, it's not good. Okay, so the next question is that, so is Huffman code optimal for any n? Right? So yeah, this question is very hard to answer. Okay, the answer is yes. So Huffman code is actually optimal for all n. Okay, so we cannot do any better. So now let's show the optimality of Huffman code. Okay, so this is not so easy to show, so we just show the binary case. Okay, and if it's not binary, then we can show that similarly. So now we just show the binary case. Okay, so in order to show that, we need some important property for the optimal code. Okay, let's see what are the property here. Okay, so yeah, let's introduce you some symbols. So again, we denote the size of this is m. So in total we have m number of source symbols. Okay, and they assume the probability vector is this p1, p2, up to pn. So now we assume ordering of those. So we assume p1 is bigger than or equal to p2, and so on. Okay, and we denote li as the code word length of the i's symbol. Okay, so now, yeah, we assume we have an optimal f. So this is a mapping with length, with length li, okay, for all the symbols, such that the length of the code here, PILI, is optimal, is minimum. Okay, yeah, those are some of our assumptions. So now let's introduce a lemma. So in order to construct an optimal code, so it have to satisfy three important property. We have a lemma here. So for any given probability P, okay, there exists an optimal code satisfying the following properties. Okay, number one property is that if the probability Pi is bigger than or equal to Pj, and then the length of the code Li has to be less than Lj. Okay, this is kind of intuitive, right? So for a code, for a symbol with a higher probability, then we should give a lower length. Okay, and then yeah, for the last one, for the code length of the code word of Cm and Cm minus 1, right? So which corresponding to the code word with the least 2 probability. Okay, for this kind of code words, so what do you think the relationship between these two lengths? Right, from the first one, we know that this guy should be bigger than or equal to this guy, right? But of course, we're not going to write that because that's included here. Okay, so basically, they are equal. Okay. So basically, if its code is optimal, we can always construct code such that they are equal. Okay, the second property. The third one is that not only their lengths are equal, so actually we can construct the code such that they are siblings. Okay, siblings basically means that they are the same for all the prefix except the last symbol. Okay, so there exists a optimal code such that Cm and Cm minus 1 are siblings. Okay, it is like in the Huffman code, right? So let's say for this one we have here is Cm, here is Cm minus 1, right? Something like that, right? So those basically call siblings, right? So these are the parents. This is a parent node. Right, and then those are the siblings. Okay. Yeah, so let's emphasize this basically called siblings. So any question? Okay, so for the optimal code, it can satisfy these three important property. Okay, let's prove it.
Actually, I have a quick question. Is
Yeah.
it possible for, like, if you had just like a general sort of code that's like tree structure or something, is it even possible to have like 3 without having 2 or something? Like
Very good.
If they're siblings, then they're...
Very good question. Yeah, so basically, probably no, right? The proof of that is that, so we need to prove the first one, and then this implies the second one, and then this implies that. Okay, so it's possible that they are not siblings, right? But the first two we cannot violate. Okay. Right, siblings is like, we can always move them, right? So, okay, very good. Yeah, let's see how we can prove that. Proof. Yeah, probably the first one is pretty straightforward, right? So how can I prove the first one? Yeah, we can basically show this, right? We can prove it by contradiction. Or, we can just argue it. It's an easy contradiction. So basically what we do is that we suppose Pi is bigger than Pj. However, LCI is bigger than or equal to LCj. Right? We want to show reverse, right? So our assumption is that, okay, so it's in the other direction, okay? And we assume Ci and J are in our code book. Okay, so if that is the case, then what do we do? Right? So if probability Pi is bigger than probability Pj, and we assume the length of I is bigger than the length of J, right? We're going to show it is not good, right? By not showing good is that, so we show there's another solution that the average length can be better. Okay, so the way we do that is we swap it. Okay, so how about we assign LCI to PJ and LCJ to PI? See what happens. Okay, so that's basically the idea. So basically what we do is that we assign CI to PJ and CJ to PI. Okay, then we just compute the length of the code. Okay, and we denote this new code is this. So assign this that, and then we get a new code C tilde. Okay, so now basically what we do is that we just want to show that the length of the C tilde minus the length of C. So this guy should be less than or equal to 0. Then we have a contradiction, right? So basically, yeah, let's just compute it. So yeah, because now the only difference between C tilde and CJ is for these two symbols, right? Everything else is the same. Okay, then if we use this minus that, so the only thing left is something related with these two symbols. Okay, so basically what is left is that for Pi, we have LCJ minus LCI, right? Because for this guy, for Pi, we assign CJ, length CJ, and for this guy, for the symbol I, we assign length CI, right? So that's one difference. And the other difference is Pj, right? For Pj, so it's vice versa. We have LCI minus LCJ. Okay, so this is what we got, and then we can combine them, right? So here we have LCJ minus LCI. Here we have LCI minus LCJ, right? So it's basically the opposite direction, right? So now we have Pi minus Pj, and then we have LCJ minus LCI, right? Okay, so now we can compare the difference here, right? For this guy, so we know Pi is bigger than or equal to Pj, so this guy is bigger than or equal to 0. Right, and for this guy, so we know Cj is bigger than or equal to Cj is less than or equal to LCI, right? Therefore, this guy will be less than or equal to 0, right? And then, so this in total we have this is less than or equal to 0, right? And then we'll have a contradiction, right? Okay, so it's not good, then so this assumption is wrong. So okay, so and then this is number 1, right? So from here we can conclude that ln C tilde would be less than or equal to this guy. Then we have a contradiction, and then number 1 is proved. Okay, so this is our number 1. So if this is bigger than that, bigger than or equal to that, then the length of I will be less than or equal to the length of J. Okay? Any questions? Okay, great. So, and from this, from here, then we can basically conclude that the C is not optimal unless the equality holds, right? And also we can conclude that the LCM is bigger than or equal to LCM minus 1, right? And bigger than or equal to all other lengths. Okay, so our number 2 is that we want to show they are the same. right? So they cannot be, so the strictly larger is not possible for these two code words, for the last two code words. Okay, again, so let's say if we assume this guy is strictly bigger than C, strictly bigger than this guy, and let's see what will happen. Okay. So yeah, let's first see that. So yeah, let's first to show so whether CM can have a sibling or not. Right? Let's say so if this guy is strictly bigger than this, so can CM has a sibling? Right? Let's say here is CM. Okay. And let's see. So whether CM can have a sibling. No, right? Because it's bigger, strictly bigger, right? Therefore, we can conclude that. So this guy cannot be a sibling. Okay, or this is not a code word. Okay, then what should they do? Right. So if this guy is not a code word, and then we have a here is a code word, right? Therefore, it's kind of weird, right? So what we can do is that we just move this guy to here. Then nothing is lost, and we save one length. Right? The length is shorter, and then nothing is lost. Is that right? Okay, then we basically can show that, right? So if this guy is true, then our conclusion is that CM, not CM, I mean the C has CM inside. So we can conclude that this is not optimal, right? Because we can always have another new code word that has a shorter length and without lose anything. Does that make sense? Okay, great. Okay, then, so number 2 is proved, right? So basically, therefore, for optimal code, the length of CM and the length of C minus M minus 1, they have to be the same, right? Then basically, that is the second one. Okay, so the third one is that so there exists optimal code such that CM and CM-1 are siblings. Okay, so now we didn't show that they are siblings, right? We just show the lengths are the same, right? But for number 3, so let's say if we have a CM, so that's here, right? For example, yeah, let's say for example, we have a CM minus 2 here. Okay, and then we know that the length of this guy is the same as this guy, right? They must on the same level, right? Therefore, we can just swap it, right? And then such that CM and CM minus 2 are siblings. That makes sense? Okay, then this is basically what we do. Okay, and then we prove the number 3. So if they are not siblings, we just swap it such that we make them as siblings. Okay, very good. Any questions? And then we prove this lemma, right? So this lemma is kind of very important. Okay, so we're going to use lemma to prove the Huffman code is optimal. So now let's recall the Huffman procedure. Okay, so yeah, so that holds for any optimal codes. Okay, so we're not talking about Huffman yet, right? So this theorem, this lemma, so this holds for any optimal codes. right? We don't assume a Huffman procedure here, right? So now let's add the Huffman procedure and see what we can get. Okay. So we assume the probability is this, right, up to Pm, right? So now we consider this as well. Okay, so what we're going to do is that we're going to perform the Huffman procedure, right, which is to combine these two to have a new probability, right? The new one is Pm minus 1 prime, right? That equals to Pm minus 1 plus Pm. Right? By doing one step of this Huffman procedure, so what we got here is another probability distribution. That's P1, P2, up to Pm minus 1 prime, instead of Pm minus 1 prime, Pm minus 1. Okay? Yes?
How do we know that Pm minus 1 prime is less likely than Pm minus 2?
Oh, it's an assumption.
Okay.
Yeah, so yeah, probably it's too far away from here. So we have this assumption, we have this ordering.
Mm-hmm.
Yeah.
But then once we do the addition, we still assume that it's smaller?
Oh, but that's good. We don't. Yeah, so yeah, for the new one, I mean, this could be higher in the middle somewhere.
Okay.
Right? So yeah, that's a very good question, right? So now for the new distribution, so this may be large. Yeah, that's right.
Okay.
Very good. Yeah, but we only need to assume the ordering here. Okay, so we don't need to show have the ordering there. Okay, so now let's do two procedures. Okay, so now let's assume that f prime. So this function, remember? So we defined this function before, right? I denote an optimal code p prime. Okay, so with length li prime. Okay, and I is from 1 to minus 1. Okay, so yeah, this is from this probability distribution, right? So what we're going to do is that we're going to expand this function f prime, and then we construct a new code for the distribution p. Okay, and then we can do the other way, right? So the first way to do it is that we have a code for this guy, so and then we assume that's the optimal code, right? And then we're going to expand this code for a code for probability p. Okay, let's see how we do this. So we expand f prime and construct a code f for p, okay, as follows. Right, so basically here what we do here is that we have f prime and m minus 1, right? We're going to expand this in this way, f and fm. Okay, and we just assign here as 0 and assign here as 1. Okay, and for all others, we assume fi and f prime I, they are the same. Okay, then we have a new code. Okay, so now let's find what is the relationship between the length of the old code and length of the new code. Okay, so basically what we're going to do is that we compute the length of the new code. So that is given by this PILI. Okay, so let's compute that. So basically, so if we do the summation from 1 to n minus 2, we have pi times l prime, because from 1 to n minus 2 they are the same for the length, right? And then we add pm minus 1. So now we have l minus 1 prime plus 1, right? Because so now for the new code, we just add one more symbol here, right? And then we need to add PM LM prime minus one plus one as well. Okay, so now let's try to combine this. So now we can, for the first term, so we can combine it with this PM minus 1 prime times L minus 1 prime, right? Because so the summation of this and that equals to this guy, right? So that's the expansion. Okay, and then we just need to add this guy and this guy at the end, right? And we can see that for what is this guy, right? So basically that's the average length for the code for P prime, right? So then this is Ln. So we put a star here because this is the optimal length. Okay, P prime. And then we add P I minus 1 and the Pn. Okay, we mark that as a star. Okay, so this is one formula. Okay, so now let's consider the other way, right? Let's denote an optimal code for P, okay, with length Li. Okay, and then we do the opposite procedure, right? So basically what we do is that we reduce F and construct a code F prime for P prime. Okay, so basically what we do is that, so now we have this guy, right? So we combine this and that. Okay, why we can do this? Because of the lemma, right? We know F is optimal, right? Then we must, so for these two, so they can be siblings, right? And then we combine this to get a new code for this. Okay, so we merge the least two symbols m minus 1 and m to get this. Okay, and we can see that, so the length of m minus 1 L m minus 1 prime, so that basically equals to L m minus 1 and equal to L m minus 1 minus 1, right? So because, so we combine it into that, so it's just one symbol less, right? And for all other i's, they are the same, so we let f prime I equals to fi, basically. Okay, so now we do the same thing, right? So now we're going to compute the length of this guy. Okay, the length of this guy is nothing but Li prime. Okay, and then, so now here is m minus 1 instead of m, right? Because we have one symbol less for the new code. Okay, then we can do pretty much the same thing as before. So now we have pi li, and then add pm plus p m minus 1, and then this guy times lm minus 1, right? So this is basically the last symbol we just combined. Okay, and from here we can see that, so if we do this summation to m, okay, so and then so this guy multiply that and this guy multiply that, so that's basically the the probability times the length for the last two symbols, and combined with the first one, so we have the length of the previous code, right, the optimal code. Okay, and then we need to here is a minus 1, then we just need to minus this and that. Okay, and this equals to ln star p minus this guy minus this guy. Okay, so we denote that as double star. So now we have two equations. Okay, so now, using from star and the double star, so we can get, so let's say we just add them two, right? So we just add them two together. Okay, so basically what we have before is this guy here, right? Is this guy equal to this, add this two, right? And now we have this guy equal to this minus this two, right? So basically what we get is that L prime plus Ln prime plus Ln, right? So that equals to Ln star P prime plus Ln star P. Okay, and the minus this two and plus this two canceled. Okay, very good. And from here, we can get, so we just move the terms to one side. So we have Ln minus Ln star P plus Ln prime minus Ln star P prime. That equal to 0. Okay, and why is magic? So because know that, so this star are the optimal code, meaning that has the smallest length. Okay, so we know this guy is bigger than or equal to 0, and this guy is bigger than or equal to 0, right? Therefore, we can conclude by doing this procedure, Ln equals to Ln star P, and Ln prime equals to Ln star P prime. Okay, then via all this complicated procedure, what we have shown? What's the meaning of it? Right now, let's recall the procedure, right? So the first procedure is that, so we have a code for this guy. And what we do is that we expand it in this way. Okay? And then what we get is Ln, right? And the other way is that, okay, so now we have a code for the original P for this guy, right? And then what we do is that we do a kind of Huffman procedure to get a new code, okay? And then the length of this code is given by this, right? So now what we show is that both Ln and Ln prime are optimal. Basically, it shows the procedure is optimal. Okay, so let's write it down. In summary, we have shown that by extending an optimal code for P prime, we obtain an optimal code for P. Okay, so this is number one. Number two, by reducing an optimal code for P, we obtain an optimal code for P prime. Okay, very good. And we don't have the time, well, okay, it's way more than 40. Okay, so probably you can think how we can, use that to show Huffman code is optimal. We're almost there, right? The last step is almost trivial. Okay, great, thank you, see you.